So for this session, we're going to talk about the thermal radiation spectrum, sometimes referred to as the black body spectrum. And we're going to look at how objects that are at a certain temperature will give off some light. And if we detect this light, we can actually work backwards to figure out what is the temperature of the object that actually emitted this light. So this thermal radiation is basically the light that is given off of an object owing to the object's temperature. If we were to look at the molecules that make up any kind of ordinary solid, those molecules and those atoms are not completely motionless. They're always going to have a little bit of vibration to them. Even in just an ordinary object like this, the atoms that make this up are vibrating a little bit. The higher the temperature of the object, the more vibration there is, the more kinetic energy those objects have. And if you take charged particles and cause them to accelerate in different ways, they will tend to give off light. And basically, a quick shorthand is the higher the temperature, the more those particles are kind of jiggling back and forth, the more radiation is going to be emitted, and the more high energy radiation is going to be emitted. So basically, any solid, liquid, or even sufficiently dense gases that are above absolute zero will emit this kind of thermal radiation. In another session, when we talk about spectroscopy, we'll talk about how thin gases under different conditions can give off different kinds of radiation. But for this one, we're going to focus on the solids, liquids, and dense gases. And again, just for quick reference, generally when we talk about temperatures in astronomy, we'll be talking about temperatures in Kelvin, where 0 Kelvin is when those particles have actually come to a stop, which never actually happens in nature. But basically 0 Kelvin is minus 273 degrees Celsius. And if I want to convert from a temperature in degrees Celsius to a temperature in Kelvin, you basically just add 273. So hopefully you've seen this before. If I have an object that I heat up a lot, say a glowing hot piece of iron, if you've ever gone camping and are cooking something on a campfire, you'll see the wood is glowing pretty brightly. If you stick a poker or something that you're going to cook marshmallows on, if you stick that into the fire, it will start to glow with the same kind of color that the wood is glowing with. The idea here is that most materials, again, for thermal radiation, we're looking at solids, liquids, and dense gases. And it's pretty much approximately the same spectrum from each one. If they're the same temperature. We're going to be talking about these perfect thermal emitters, and these don't actually occur very often in nature, but it's going to be a good enough approximation, again, for most of these solids, liquids, and dense gases. So basically, everything in the room is at pretty much the same temperature. So if I was to use a thermal camera, everything in the room is at the same temperature, so it's giving off pretty much the same radiation. Now, me as a warm-blooded person, as a warm-blooded mammal, my body temperature is probably a little bit higher than the temperature in the room. So I would be at a different temperature. I'm giving off a little bit different thermal radiation, a little bit more light at a little bit higher energies. And again, we're going to look at some of these cases. I have a little toaster oven over here that we're going to play around with and actually look at one of these thermal spectra. But before we do that, just think of looking at, say, the coils of a toaster. Or if you have a oven that has, the old style kind of metal gratings, if you raise the temperature of that very, very much, what sort of colors do you tend to see? Well, when you're heating up these objects, most of the time at the very beginning, it's not giving off any visible light. Before you actually turn on an oven or turn on the coils of a toaster, it's at approximately room temperature and it's not giving off any visible light. But as the coils heat up, what you'll notice is at first, the color that you see is this kind of deep, deep red. In fact, there's a simulation that we can kind of play around with. This is one of the PhET simulations, PhET. So if you search for PhET black body spectrum or thermal spectrum, you'll be able to kind of play around with this simulation where I can change the temperature of the object and I can look at what spectrum of light I'm going to get. How much light in each part of the spectrum. So we've got the visible part of the spectrum. This over here would be the infrared part of the spectrum, longer wavelengths than visible light. This part over here would be the ultraviolet part of the spectrum, the UV part of the spectrum at shorter wavelengths. And if we started with a very, very low temperature object, let me just zoom in on this so we can actually see some of those features, then basically it's not giving off any visible light. But as I raise the temperature, and I zoom out a little bit, we're going to be giving off more and more infrared light. So the first thing that's emitted is just infrared light. And as I raise the temperature, notice the first color that we're going to start to see in the visible part of the spectrum is going to be a little bit of red light. So the first thing that we see is this deep red color. So at lower temperatures, looking at the slides, at lower temperatures, most of what we see is this infrared light, but that's not, our eyes aren't sensitive to that. So the first colors we see is this deep red. As we raise the temperature, well, now I'm not only giving off red light, but it's also giving off a little bit of yellow light, a tiny bit of green light. And to our eyes will see that as being kind of an orangish color, starting to glow orange. And as we continue to increase the temperature, a couple of things are happening. First, the amount of light given off is increasing dramatically. It's getting much brighter as we raise the temperature. And the exact colors of light that are being emitted are going to be a little bit different. We started with this just red light, this deep red, and now we're giving off a little bit of yellow light, a little bit of green light, so we're getting this kind of orange as well. The red's still the dominant one. And as we continue to raise the temperature, this spectrum is giving off more and more short wavelength light. So this graph is shifting towards shorter wavelengths, and that is causing the perceived color to change in some of these different ways. And this is characteristic, again, of any solid, liquid, or dense gas. These thermal emitters are all pretty well described by this image until if we go up to the temperature of the sun, well, the sun gives off lots of light across the entire visible spectrum, so we perceive that as white light. And if we cranked up the temperature even higher, and again, have to zoom out a lot, if we crank up that temperature, we are still giving off some infrared light. We are still giving off a lot of visible light, but we're giving off even more ultraviolet light. When we talked about the properties of light, I said very high mass, very energetic stars that have these very high temperatures are giving off a huge amount of ultraviolet light. That's also an effect of this thermal radiation. So let's see if we can summarize this. So this graph, again, is looking at how much light are we looking at in each part of the spectrum. How much red light am I getting? How much yellow light? How much blue light? How much infrared light? How much ultraviolet light? So again, the higher the part of the graph, the more intense the radiation at that wavelength. And one of the things about these thermal radiation spectra is we get this smooth shape for these thermal spectra, where the higher the temperature, first, the taller the graph overall, so taller graph, more light. The taller the graph, because of just more light being given off across all wavelengths. And we also have the peak of that graph shifts to shorter wavelengths. So peak emissions at shorter wavelengths. And this changes the color. And remember that shorter wavelength light corresponds to a higher amount of energy per photon. So this is the overall pattern. And let's actually try this with my particular setup and with the toaster so we can actually see this happening in real time. Okay, so I've got two views. My camera view is just showing, okay, I'm turning on this toaster oven. We're going to see the thing heat up inside. In fact, I'm going to put the camera down here so we can see inside of there a little bit better. Let me get some of my other stuff out of the way. And this view shows what I'm seeing through the spectroscope. So hopefully, if this works well enough, we should be able to see the red light start to form as this thing is just starting to heat up. And then we're going to get more and more wavelengths of light showing up brighter and brighter. So I'm going to turn this on. Hopefully this is aligned properly. I set this up ahead of time, so hopefully this will work. And again, on my camera view, we should start to see this thing starting to glow red a little bit. Okay, I'm just starting to see a little bit of redness there. And on here, make sure this doesn't time out on me. We're starting to see a little bit of redness show up. Again, it's kind of dim at the beginning. But as this thing is getting hotter and hotter, it's getting brighter overall. And now we're starting to see mostly red and a little bit of yellow light, even a little bit of green light mixed in there. And again, as the temperature continues to increase, we're still at the point where we're getting mostly red light. We're not really getting any blue light over here. Mostly red light, a little bit of yellow light, a little bit of green light. And we can see that overall effect of this thing the element inside has gotten very, very hot. So it's glowing with that bright red color. Still not getting any blue on here because it's not reaching totally unsafe levels of brightness in there. So again, this is an example that you can kind of observe on your own, saying, I can look at the coils of a heater and watch it give this nice, smooth, continuous spectrum. So now, one side topic that I failed to mention before, these kinds of filters that you can use to break up light and even small spectroscopes, you can get small, cheap spectroscopes that work pretty well for actually making some basic observations for about $10 at certain science equipment suppliers. Professional grade spectrographs and spectroscopes, they can easily go into the many tens of thousands of dollars, but again, you can get example versions of that for pretty cheap if you want to try making some of these observations yourself. So with this thermal radiation, again, for solids, liquids, and dense gases, they'll produce all sorts of different colors of light, this smooth, continuous spectrum. And the reason for this is when we have solids and dense gases, the way that light is absorbed and emitted in many cases depends on what kind of transitions the electrons inside of those atoms, what sort of transitions those electrons can go through. If we have a low density gas and there's only a few electron energy levels available for those electrons, there's not very many transitions that those electrons can go through. In one of the next sessions, when we talk about spectroscopy, we're going to talk about these low density gases and look at exactly what transitions the electrons can go through, how they can absorb and emit light. And there's not going to be as many options. It'll absorb and emit light at certain wavelengths and no other ones. But for this thermal radiation case, since the atoms and the molecules that make up these solids and liquids are kind of packed together so tightly, those electrons can jump around modified energy levels. They can jump from one atom to another. There are basically a huge number of different kinds of transitions that those electrons can go through, which means they can absorb and emit lots of different energies of photons, lots of different wavelengths of light. And that's what gives us this nice smooth shape for the spectrum. So again, we get this continuous spectrum, and the basic patterns that we get is, depending on the temperature, this radiation will max out in different parts of the electromagnetic spectrum. At low temperatures, you're mostly going to be giving off infrared light. At the temperatures of certain kinds of light bulbs and of, say, the sun, most of the energy is going to be given off in the visible spectrum. For very high temperature stars, well, those peak emissions are going to keep going to shorter and shorter wavelengths, and that might max out in the ultraviolet. Or if you have temperatures in the millions of degrees, or I should say in the millions of Kelvin, then that could actually be giving off its peak in, say, the X-ray part of the spectrum. But again, this general pattern for objects where we've raised the temperature of that object. We call this a thermal radiation spectrum, also known as a black body spectrum, because objects that are very dark in color are generally closer to being those perfect thermal emitters. Charcoal would be a good example of something very close to being a perfect thermal emitter. So this is the same kind of graph. Again, the general overall shape of this graph, I should draw this out just so for a quick reference. If this is wavelength, again, we have that Greek letter lambda to basically describe the wavelength, and basically the brightness at that wavelength. So brightness or intensity. If we have, say, the ultraviolet part of the spectrum, the visible part of the spectrum, and the infrared part of the spectrum, if I have a low temperature object, then it's not going to be giving off very much light, and most of the light that it's giving off is going to be in this infrared part of the spectrum. So this would be kind of lower temp. If I raise that temperature a little bit, if that temperature goes up a little bit, then, oh, maybe it's giving off some yellow light, some red light, still not a huge amount, but this might be a mid temperature. And if I crank the temperature up a lot, well, now I'm giving off lots of visible light, maybe even some ultraviolet light, and this would be high temperature. And again, this is going to be pretty accurate for both solids, liquids, and dense gases. So if I look at the spectrum of light from some object, and again, this is the same kind of graph, just a different way of scaling it. If I look at that same kind of graph of a particular object, I can match it up with one of these graphs and use it to determine, well, what is the overall, what is the temperature of that object? If it's only infrared, it's probably pretty low temperature. If it's giving off some red light as well, okay, that's going to be hotter. If it's giving off, a lot of ultraviolet light, it's going to be a very high temperature object. So again, in this graph, we've got a 310 Kelvin human, basically just giving off infrared light and essentially no visible light at all. The sun is giving off a lot of light across the visible spectrum. So we see the sun's light as being white. And again, the higher temperature star is peaking in the ultraviolet. Now, when we look at sunlight in detail, the sun's light is not a perfect thermal radiation spectrum. It has this overall pattern of swooping up, reaching a peak, and then gradually swooping back down. But it's got lots of these other little kind of features where certain colors seem to be missing. There are drops in brightness at some of these particular wavelengths. We're going to talk about these when we talk about spectroscopy, and all of these little lines on here, these wavelengths of light that are missing, this gives us a huge amount of information about the properties of the object that is emitting this light. So again, we'll talk about those finer details later on, but at least for now, we still get this overall picture of the intensity swoops up at certain wavelengths and then gradually swoops back down And if I know that peak, where that peak is showing up, at what wavelengths that peak is showing up, we can figure out what the temperature of the object is. You may have heard that incandescent light bulbs, the old style of light bulbs, aren't very energy efficient. And basically the way that those old style light bulbs work is by having a little filament in there, a little piece of wire that is heated up so much that it just starts glowing very brightly. The problem is with those incandescent bulbs, as you raise the temperature, eventually you start giving off some visible light, but there's a huge amount of energy that's just given off as infrared light, which our eyes are not sensitive to. All it does is start to heat up the room around it. And for those old style incandescent bulbs, about 75% of the energy is just given off as infrared light, which is kind of useless to us. If it's winter, it'll help to heat your house, but in summer, that's kind of a really bad thing. Modern bulbs, modern higher efficiency, say LED bulbs, are specifically designed to generate their light in a different way, so it only gives off visible light and doesn't give off much or any infrared light, which is kind of just wasted. And again, extremely high temperature stars, they might peak in the ultraviolet. In systems where materials are heated to literally millions of Kelvin, that might even give off X-ray light. So let's say I look at these two stars. This is Sirius A and Sirius B, and this is specifically looking at the X-ray light. Sirius A is actually a much, much larger star than Sirius B. We're going to talk about these different types of stars later on, but Sirius B in this X-ray image looks really, really bright because it is incredibly hot. It's very small, but incredibly hot. So Sirius B is actually giving off a significant amount of its energy in the X-ray part of the spectrum. So in one of the next sections, we'll talk about how to quantify this, how we can actually look at the spectrum and specifically measure what is the temperature of the object if it's giving off this particular light. So we'll do that in one of the next sections.